If the first time you listen to this, some of these concepts seem a little bit hard to grasp, don't worry about it. As we continue and as we move on with this course, they'll start to make more sense when you see them used in real examples. I definitely would recommend going back and rewatching and re-listening to the parts that you don't quite get and asking questions in the discussions tab of the GitHub repository.
Awesome. So now that we know all the cryptography pieces and all the little nitty-gritties of how the blockchain actually works and how our signatures work and how everything sticks together, let's talk a little bit about how this works in actuality and what's really going on. Now, for a lot of this, each different blockchain has slightly different algorithms and slightly different metrics and criteria for doing a lot of this stuff. So when we're talking about these specific implementations, keep in mind the exact algorithm might be a little bit different, but the concepts are all still going to be exactly the same. Hashing and a hash function is going to be the same no matter where you look. A decentralized blockchain is going to be the same no matter where you look. How it's actually implemented is going to be a little bit different. Now, traditionally, when you run an application, be it a website or something that connects to some server, you are interacting with a centralized entity. And unlike how we saw with the blockchain with multiple different peers, it's going to be run by a single centralized group. Now, it still could be run on many different servers, but all those servers are still going to be controlled by the same centralized group. Blockchains, as we saw, run on a network of different independent nodes. When we saw peer A, peer B, peer C, those were different examples of different independent users running the blockchain technology on their own node. Now, when I use the term node, I'm usually referring to a single instance of a decentralized system. So when I say a single node, when I'm talking about a blockchain, I'm talking about one of those peer A's, peer B's, peer C's running that blockchain software. I'm talking about one server running this technology. And again, it's this network, it's this combination of these nodes interacting with each other that creates this entire blockchain. What makes these so potent too is that anybody can join the network, and that's why there's decentralized. The barrier to entry is a little bit of hardware requirements, you getting the correct materials to run the software, and then you running the software. Anybody can join these networks and participate, and that's what makes it truly decentralized. In fact, you can go to GitHub right now and run your own Ethereum node in a few seconds. Now, in the traditional world, applications are run by centralized entities. And if that entity goes down, or is maliciously bribed, or decides that they want to shut off, they just can't, because they're the ones that control everything. Blockchains, by contrast, don't have this problem. If one node or one entity that runs several nodes goes down, since there are so many other independent nodes running that it doesn't matter. The blockchain and the system will persist so long as there is at least one node always running. And luckily for us, most of the most popular chains like Bitcoin and Ethereum have thousands and thousands of nodes. And as we showed in our demo, if one node acts maliciously, all the other nodes will ignore that node and kick that out or even punish it in some systems, because they can easily check everybody else's node and see, okay, this one is out of sync with the majority. And yes, majority rules when it comes to the blockchain. Each blockchain keeps a full list of every transaction and interaction that's happened on that blockchain. And we saw if a node tries to act maliciously, then all their hashes are going to be way out of whack and they're not going to match everybody else. This gives blockchains this incredibly potent immutability trait where nothing can be changed or corrupted. So in essence, we can think of a blockchain as a decentralized database. And with Ethereum, it has an extra additional feature where it also can do computation in a decentralized manner. Now let's talk consensus, proof of work, and proof of stake, because you've probably heard these before and they're really important to how these blockchains actually work. When we went through that blockchain example and we did that mining feature, this is what's known as proof of work. Proof of work and proof of stake fall under this umbrella of consensus. And consensus is a really important topic when it comes to blockchains. Consensus is defined as the mechanism used to reach an agreement on the state or a single value on the blockchain, especially in a decentralized system. I briefly alluded to this consensus mechanism in our blockchain example when I said if one changes something and the other two don't, then majority will rule and kick that one out. This is part of that consensus mechanism. Now, very roughly, a consensus protocol in a blockchain or decentralized system can be broken down into two pieces: a chain selection algorithm and a Sybil resistance mechanism. That mining piece that we were doing, or the proof of work algorithm, is what's known as a Sybil resistance mechanism. And this is what Ethereum and Bitcoin currently use. Please note that depending on when you're watching this, If ETH2 is out, then it's no longer proof of work. Now, proof of work is known as a Sybil resistance mechanism because it defines a way to figure out who is the block author. Which node is going to be the node who did the work to find that mine and be the author of that block so all the other nodes can verify that it's accurate. Sybil resistance is a blockchain's ability to defend against users creating a large number of pseudo-anonymous identities to gain a disproportionately advantageous influence over said system. And in layman's terms, it's basically a way for a blockchain to defend against somebody making a bunch of fake blockchains so that they can get more and more rewards. Now, there are two types of the Sybil resistance mechanisms that we're going to talk about here, namely proof of work and proof of stake. Let's talk about proof of work a little bit more in depth first. In proof of work, this is Sybil resistant because a single node has to go through a very computationally expensive process called mining, which we demonstrated earlier, to figure out the answer to the blockchain's riddle of finding that correct nonce or whatever the blockchain system has in place. In proof of work, this works because no matter how many pseudo-anonymous accounts you make, each one still has to undergo this very computationally expensive activity of finding the answer to the proof of work problem or the proof of work riddle, which again, in our demonstration, it was finding a nonce with that first 4 zeros. But again, each blockchain might change the riddle or change the problem to be a little bit different. In fact, some of these blockchains make this riddle intentionally hard or intentionally easy to change what's called the block time. The block time is how long it takes between blocks being published, and it's proportional to how hard these algorithms are. So these problems actually can change depending on how long they want the block time to be. If a system wants the block time to be very, very long, they just make the problem very, very hard. If they want it to be very short, they make the problem a lot easier. We'll talk about Sybil attacks in a little bit and how they can affect the system. But with proof of work, it's a verifiable way to figure out who the block author is and be Sybil resistant. Now, you need to combine this with a chain selection rule, create this consensus. Now, there's some consensus protocols that have more features, but very, very roughly, these are the two pieces that we're going to look at. The second piece is going to be a chain selection rule. How do we know which blockchain is actually the real blockchain and the true blockchain? Now, on Bitcoin and Ethereum, they both use a form of consensus called Nakamoto consensus. And this is a combination of proof of work and longest chain rule. The decentralized network decides that whichever blockchain has the longest chain or the most number of blocks on it is going to be the chain that they use. This makes a lot of sense because every additional block that a chain is behind, it's going to take more and more computation for it to come up. That's why when we saw in our transaction, we actually saw confirmations. The number of confirmations is the number of additional blocks added on after our transaction went through in a block. So if we see confirmations as 2, it means that the block that our transaction was in has 2 blocks ahead of it in the longest chain. Now, I do want to point out that a lot of people use proof of work as a consensus protocol, and I do want to say that this is a little bit inaccurate, but sometimes people use it interchangeably. Proof of work is a piece of the overall consensus protocol, which in Bitcoin and Ethereum 1's current case is Nakamoto consensus. Nakamoto consensus is a combination of proof of work and this longest chain rule, both equally and very, very important. Now, proof of work also tells us where these transaction fees and these block rewards go to. Remember how when we made this transaction, we had to talk about gas and a transaction fee. So who's getting paid? Who is getting this transaction? And this transaction fee is going to the miners or the validators. In a proof of work network, they're called miners, and in the proof of stake network, they're called validators. They are a little bit different, and we'll get into that when we talk about proof of stake. In this proof of work system, all these nodes are competing against each other to find the answer to the blockchain riddle. Remember, in our example, it was to find a hash that has 4 zeros at the start. And again, depending on the blockchain implementation, that riddle is going to be a little bit different. But all the nodes are trying as many as possible to try to get this answer first. Why? Because the first node to figure out the answer to the blockchain riddle is going to get that transaction fee. They're going to get paid from that. Now, when a node gets paid, they actually get paid in 2 different ways. One is going to be with a transaction fee, and another piece is going to be the block reward. Remember how we talked about alternating the gas price or the GUI on our transaction? Well, that's the transaction fee that we're going to pay to these blockchain nodes for including our transaction. The block reward is given to these nodes from the protocol, from the blockchain itself. You've probably heard of the Bitcoin halving before. The halving is referring to this block reward getting cut in half, and it's supposed to be cut in half roughly every 4 years. this block reward increases the circulating amount of whatever cryptocurrency that is being rewarded. For example, on Ethereum, the block reward is giving out Ethereum, and on Bitcoin, the block reward is giving out Bitcoin. So these nodes are competing against each other to be the first one to find this transaction, to be the first one to find the answer to this problem, so that they can be the ones to win both this block reward and your transaction fee. Some blockchains, like Bitcoin for example, have a set time when they're no longer going to give out block rewards, and the miners or the nodes are only going to get paid from transaction fees. Now, this gas fee, again, is paid by whoever initialized the transaction. When we got our funds from the faucet, there was some server and somebody else was paying the transaction fee for us. However, when we sent Ether from one account to another, our first account actually paid some transaction fee to send that Ether. In proof of stake, there's also a gas fee, but it's paid out to validators instead of miners, and we'll talk about that in a little bit. Now let's talk about two types of attacks that can happen in these blockchain worlds. Let's talk about the first one being the Sybil attack. The Sybil attack is when a user creates a whole bunch of pseudo-anonymous accounts to try to influence a network. Now, obviously, on Bitcoin and Ethereum, this is really, really difficult because the user needs to do all this work in proof of work or have a ton of collateral in proof of stake, which again, we'll talk about in a bit. The other more prevalent attack is what's known as a 51% attack. Now, as we saw as part of our consensus protocol, these blockchains are going to agree that the longest chain is the one that they're going to go with, so long as it matches up with 51% of the rest of the network. This means that if you have the longest chain and you have more than 51% of the rest of the network, you can do what's called a fork in the network and bring the network onto your now longest chain. Now, Sybil attacks obviously are when a single node or a single entity tries to affect the decentrality of the network by pretending to be multiple different people, although they're just the same person or entity. And like I said, it's really difficult to do in proof of work and proof of stake. So you can see now that blockchains are very democratic. Whichever blockchain has the most buy-in and is the longest is the blockchain that the whole system is going to corroborate. When nodes produce a new block and add it to the longest chain, the other nodes will follow this longest chain that the rest of the network is agreeing with, add those blocks to their chain, and follow up. So very small reorganizations are actually pretty common when a blockchain picks a block from a different longest chain, puts it on, and then has to swap it out for another block and continue with a different blockchain. However, if a group of nodes had enough nodes or enough power, they could essentially be 51% of the network and influence the network in whatever direction that they wanted. This is what's known as a 51% attack, and it's happened on blockchains like Ethereum Classic, which is not Ethereum. This is why the bigger a blockchain is, the more decentralized and the more secure it becomes. So after you watch this video and you become a blockchain engineering expert, I definitely recommend you run a node as well, because you are going to increase the security of the network as a whole by running a node. So proof of work is fantastic because it allows us to very easily protect against these Sybil attacks and keep our blockchains decentralized and secure. However, it has some drawbacks as well. Proof of work costs a lot of electricity because every single node is running as fast as they can to win this race to get the rewards. This leads to, obviously, an environmental impact. Now, since proof of work and Nakamoto consensus, a lot of other protocols have taken this idea and gone in a different direction with a different Sybil resistance protocol. A lot of them with the intention to be a lot more environmentally friendly. And the most popular one right now is proof of stake. There are some chains that are already using this proof of stake protocol and that are live and thriving. Some of them are like Avalanche Solana, Polygon Polkadot. So let's talk about proof of stake now. Again, this is a different Sybil resistance mechanism. Instead of solving this difficult problem, proof of stake nodes put up some collateral that they're going to behave honestly, aka they stake. In the example of Ethereum 2, nodes put up some Ethereum as a stake that they're going to behave honestly in the network. If they misbehave in the network, they are going to be slashed or removed some of their stake. Obviously, this is a very good Sybil resistance mechanism because if you try to create a whole bunch of anonymous accounts, then each one of those accounts, you have to put up some stake. And if you misbehave, you're going to run the risk of losing all the money that you put up as collateral. In this system, miners are actually called validators because they're no longer binding anything. They're actually just validating other nodes. Now, unlike proof of work, which every node is racing to be the first one to find the block, in proof of stake, nodes are actually randomly chosen to propose the new block. And then the rest of the validators will validate if that node has proposed the block honestly. As we saw with our cryptography lesson, it's usually very easy for other nodes to verify if a proposal or a transaction is honest. Now, proof of stake obviously has some pros and cons as well. Pros are that, again, it is a great Sybil resistance mechanism and a great way to figure out who the author of a block should be. The other pros are that it's way less computationally expensive to figure out the new block, because instead of every single node on the network trying to do this, only one node needs to do this. And then the rest of the nodes just need to validate it. The cons are that it's usually considered a slightly less decentralized network due to the upfront staking costs it costs to participate. Now, this gets into a little bit of a philosophical battle on how decentralized is decentralized enough, and I think that's up to the community to decide. And as we progress, I think we'll learn more and more about how decentralized is decentralized enough. The general consensus amongst blockchain engineers, though, is that proof of stake is very, very decentralized and very secure. Now, there's another term that might be the first time you heard it, a layer 1. We're going to talk about layer 1s and layer 2s in terms of scalability really quickly as well. A layer 1 refers to any base layer blockchain implementation. Bitcoin's a layer 1, Ethereum's a layer 1, Avalanche is a layer 1. These are the base layer blockchain solutions. A layer 2 is any application that is added on top of a layer 1, added on top of a blockchain. Some examples of layer 2s are going to be Chainlink, Arbitrum, or Optimism. Arbitrum and Optimism are very interesting because they are layer 2s that also look to solve this scalability issue. Arbitrum and Optimism are what's known as rollups, and they roll up their transactions into a layer 1, like Ethereum. We're not going to go too deep into rollups and how they actually work, but all you really need to know is that they solve some of the scalability issues by being another blockchain that people can make transactions on, still on kind of this base Ethereum layer. Now, they're different from sidechains because sidechains derive their security from their own protocols. Rollups derive their security from the base layers. So Arbitrum and Optimism, for example, is going to be just about as secure as Ethereum. There's some fantastic guides in there that go a little bit deeper into rollups, and I've left a link in the description for you. All right, so we just talked about a lot of stuff. So let's do a quick recap before moving on. Sybil attacks are prevented due to protocols like proof of work and proof of stake. 51% attacks grow increasingly harder with the size of blockchain, so you should run a node. Consensus is the mechanism that allows a blockchain to agree upon what the state of the blockchain is. Sharding and rollups are solutions to scalability issues on layer 1s. A layer 1 is any base blockchain implementation, like Bitcoin or Ethereum. A blockchain scalability problem is that there's not always enough block space for the amount of transactions that want to get in them. This leads to very high gas prices. And again, gas prices are how much it costs to interact with a blockchain. Whew.
So that's it for the blockchain basics and the blockchain explainers. With just this information, you now can go off into the world and start working with blockchains and interacting with blockchains with at least some level of knowledge as to what's going on. You should be incredibly proud of yourself for just making it this far. Definitely be sure to give yourself a pat on the back and a round of applause. Now that we've gotten a lot of the basics and the fundamentals out of the way, let's start jumping into the coding aspect. This is where you're going to learn how to actually build these smart contracts, how to build these trust minimized agreements in these blockchains and in these smart contract platforms. This next section, this Solidity basics, the Solidity fundamentals section, will give you all the skills to start actually coding Solidity and understanding how these smart contracts work underneath the hood. So at this point, absolutely give yourself a high five, maybe say hi in the GitHub discussions, maybe say hi in the community on Twitter, on Reddit, etc., and be proud of just making it this far. The journey has really only just begun, but you've already learned so much. Let's begin the next section and let's jump into the code.